Hi, my name is Brian Parno, and on behalf of my colleagues at Carnegie Mellon, Microsoft Research, and INRIA, I'd like to tell you about our work on the EverCrypt crypto provider. These days, nearly every security-sensitive application relies fundamentally on cryptography. However, few applications write their own cryptographic code. Instead, most rely on a cryptographic provider like OpenSSL, Bouncy Castle, or libsodium. Because we want our money quickly and our online meetings to Zoom, we expect our crypto to be fast. Because of this, modern crypto providers like OpenSSL work heroically to get every last ounce of speed they can, and the results are very impressive. Unfortunately, crypto is hard to get right, and even harder when you add the complexity necessary to get good performance. Hence, it's not surprising that vulnerabilities are regularly discovered. OpenSSL's crypto library, for example, had 24 in just 3 years. And if you start reading about these bugs, you'll notice that they are really subtle and hard to find. And of course, the security of your application depends on the security of your crypto provider. Fortunately, in the last 5 years, we've seen some exciting results applying formal verification techniques to prove the correctness of cryptographic algorithms and implementations. Some even prove that the code doesn't leak secrets through various side channels like timing or memory. There's actually been enough activity in this space to justify an entire SOK paper. It seems like this should be enough to definitively rule out any future problems with crypto providers. Unfortunately, if you dig a bit deeper, you'll find that while existing work provides a lot of insights into how to verify crypto, it still leaves a lot to the end user. Some work only verifies a portion of an algorithm, but not the full crypto routine. For example, fiat crypto gives you verified elliptic curves, but not their use in an actual cryptographic routine. Some work gives you one algorithm, like SHA-256, which is great unless you want SHA-224 or SHA-512. In some areas, you have lots and lots of choices, for example, elliptic curves. In others, you have almost none, for example, RSA. So instead of getting the car you wanted, you get maybe half a steering wheel, one muffler, and a whole lot of tires, but no seat or engine. Even if you cobble something together, all of these are verified against different specifications using different tools, and the performance can lag state-of-the-art crypto by orders of magnitude. This state of affairs is what motivated us to develop EverCrypt. EverCrypt aims to be comprehensive so that it can support all of your cryptographic needs. It offers a modern API designed to reduce developer errors and adapt to changes in the cryptographic landscape. And crucially, it was developed from the start with performance in mind. Let's start with comprehensive. EverCrypt offers all of the basic primitives you might want, as well as more advanced constructions built on top of them, including simple high-level APIs like Box that were pioneered by the NaCl crypto library. Note that while we benefited from our prior experience developing the Hackle-Star library and Veil-based crypto, nearly all of these were freshly implemented for EverCrypt. As a result, we have developed the world's largest verified crypto code base, over 124,000 lines of code and proof, which in turn compiles to a substantial amount of C and assembly code. Our paper shares some of the techniques and lessons that we learned in the process of scaling up to a verified code base of this size, which I will try and touch on in the remainder of this talk. In designing EverCrypt's API, we learned from other crypto providers like NaCl and expanded these ideas in the context of verification. Modern crypto API design actually has numerous facets, and I'll try and step through each of these in the upcoming slides. First, a modern crypto provider should offer an agile API, which makes it trivial to swap between different algorithms that provide the same cryptographic functionality. This means that client code is programmed against a single unified API, for example, for authenticated encryption, and the client code can remain unchanged even if we upgrade from AES-CBC and HMAC to something more modern, like Cha-Cha-Poly or AES-GCM. Similarly, for hash functions, there are many possible hashing algorithms, and we may want to upgrade from something like SHA-1 to something more modern and secure. Such upgrades may come in reaction to new advances in cryptanalysis, new hardware acceleration opportunities like AES-NI, or new advances in computation like quantum computers. Abstraction, on the other hand, hides as many details as possible from the client, both about internal code details as well as internal data representations. This ensures that clients will not rely on the specifics of any given algorithm, which means their code will work for any current or future hash function. It also leads to better proof automation, as verified clients don't have their context polluted by extraneous details about the core guts of, for example, SHA-256. After all, the implementation and proof of correctness for an application like a Merkle tree should not depend on such details. Concretely, our generated C API for hashing looks something like this. The client sees an abstract state type, but not its internal representation. The client can choose which algorithm to use when creating the state, but from then on, the exact same API to initialize the state, to compress additional data into the state, and to finalize the hash into an output buffer is used regardless of the algorithmic choice. As a result, migrating to a new hash algorithm only requires a one-line change in the call to hash create. In terms of usability, EverCrypt's API offers clean, fully specified APIs to verified clients. In this way, it can serve as a foundation for verified applications such as a verified Merkle tree or a fully verified TLS implementation. However, it also offers an API in C to make it easier to integrate into existing code. Instead of relying on proof-level preconditions, the C API includes defensive runtime checks to protect against developer errors. For example, the hash API buffers partial data internally and protects the developer from misusing the standard initialize, update, finalize state machine. The API, as well as the C code we produce, also goes to great lengths to be C idiomatic. It looks similar to human-generated code, including comments. It returns proper error codes, and it uses double pointer callee allocated out parameters. It also comes with proper packaging and build scripts to simplify installation. Internally, we use tools that our team has developed to write verified C-like code for portability across platforms, and verified assembly code to squeeze out maximum performance on specific platforms. But this raises the question, how can we connect proofs about code in C and code in assembly? While we think of C as a relatively low-level language, it's actually quite different from assembly. For example, verified C code typically treats memory as structured and well-typed, while assembly views memory as a flat array of bytes. When verifying code for the absence of leakage, some verification styles are better suited to C, while others are better suited for assembly. Even the standards for calling from C into assembly vary depending on your operating system and your hardware. Finally, for verification purposes, to connect proofs written at the assembly level to those at the C level, we need to be able to translate pre- and post conditions written in machine-level terms to conditions written at the level of C. Let's take a look at those last 2 points in a bit more detail. In our work, we take advantage of F*** support for dependent types to write a single description for the semantics of calling from C into assembly. This description is generic over the number of arguments that are passed, but it ensures, through dependent typing, that each argument has the right type. It's also generic over the calling convention used, but ensures that arguments are passed according to convention, that caller-saved registers are really saved, and so on. As a result, we currently support 3 different calling conventions, and we're able to take advantage of this automated support to write 31 different interoperation points between C and assembly. However, this higher-order approach can lead to poor performance if done naively. For example, it would require carting around extra runtime state to keep track of the algorithm in use, and potentially branching on that state for every low-level operation, even single instruction operations like bitwise AND. Instead, we carefully apply partial evaluation and inlining inside of our proof tool to produce customized implementations that execute like low-level imperative code, but are still verified. When extracting, for example, compress 256, our proof tool, F***, will partially evaluate the generic compress function on the constant representing the SHA-256 algorithm. Along the way, it will eventually encounter the implementation of bitwise AND, shown above, and reduce it to simply a 32-bit AND. By the time all reduction steps have been performed, there are no higher order code remaining, and all functions and types that were parameterized over our choice of hash algorithm have disappeared. This leaves specialized implementations for the types, operators, and constants that are specific to SHA-256. These can then be compiled to efficient idiomatic C code. Crucially, our emphasis on a clean, agile API does not turn out to sacrifice performance. Indeed, EverCrypt's performance matches or exceeds the performance of state-of-the-art implementations, verified or unverified. For example, this graph shows our performance computing SHA-256. The x-axis shows increasingly large messages provided as input to the hash function. The y-axis shows the average cycles per byte to compute the hash, so lower is better. Notice that our portable implementation, shown on the left in purple, is consistently beating OpenSSL's portable version, shown in green. The blue and orange bars show targeted implementations. That is, both the EverCrypt and OpenSSL implementations are using handwritten assembly that exploits Intel's SHA acceleration instructions. We can see that both implementations provide equivalent performance, and they noticeably outperform the portable versions, showing the advantages of targeted implementations. We see a similar story when looking at targeted versions of authenticated encryption, or AEAD. Here, the x-axis shows authenticated encryption for increasingly large messages, while the y-axis shows performance in cycles per byte encrypted. So once again, lower is better. For each message size, we show two variants of AES, as well as OpenSSL's targeted version of Cha-Cha-Poly. Our first observation is that all of the AES implementations consistently outperform Cha-Cha-Poly, thanks to their use of Intel's AES-NI instructions. The second observation is that EverCrypt, shown in blue, is consistently matching or beating OpenSSL's performance, shown in orange. And for large enough messages, both versions required less than 1 cycle per byte to provide authenticated encryption. Achieving parity with OpenSSL required implementing and proving the correctness of some of their truly gnarly assembly code. This code involves reasoning about operations over a large Galois field and makes heavy use of SIMD instructions operating over 128-bit XMM registers. It performs both AES counter mode encryption and Galois counter mode authentication in a single pass, but it runs the AES op portion 12 blocks ahead and interleaves the instructions for both to achieve better processor pipelining. Historically, a subtle bug in these calculations nearly made it into OpenSSL's master branch, where it would have allowed an attacker to produce arbitrary message forgeries. Fortunately, EverCrypt's version is mathematically proven to be free of such mistakes. On the asymmetric side, the elliptic curve, curve 25519, is a popular choice these days, and it is used, among other places, in TLS 1.3. This table summarizes the performance of various implementations of the core operation of computing a point multiplication. Performance is measured in CPU cycles, so smaller is better. Amongst the implementations, verified implementations are shown in green and unverified in red. Notice that EverCrypt's verified portable implementation, shown in the middle of the table, beats prior portable implementations and even some assembly implementations, while our targeted version, shown at the bottom of the table, outperforms all prior work. To evaluate whether these performance improvements translate to the application layer, we developed a number of additional verified functionalities and applications. These ranged from simple constructions like HMAC to complex transport encryption for the quick network protocol. Each of these build on EverCrypt's agile multiplexed API, which greatly simplified the necessary application proofs. It also makes it trivial to switch to new algorithms without changing any code or proofs at this layer. Similarly, as we add new targeted implementations for better performance, all of these applications transparently benefit from these improvements. As a concrete example, we developed a fully verified Merkle tree library that's agnostic to the choice of underlying hash function. The implementation relies on incremental construction that's designed to provide high-speed amortized insertions. It's important to note that Merkle trees aren't as simple as they appear. For example, it took 3 years to uncover a design flaw in the Merkle tree used by Bitcoin. In contrast, we prove our Merkle trees are both correct, in the sense that the trees are constructed correctly, and secure. We prove security in F* by showing that if an adversary can find a collision between two Merkle trees, then we can immediately derive a collision on the underlying hash function. In terms of performance, we can handle 2.5 million insertions per second, regardless of the tree size, shown on the x-axis. In comparison, Bitcoin's implementation handles less than 1 million insertions per second, meaning we're almost 3 times faster than Bitcoin's unverified implementation. EverCrypt is still young, but portions of it are already in use in the wild. Early adopters include Mozilla, Microsoft, and just recently, the Linux kernel. Before I conclude, I'd like to mention that EverCrypt was developed in the context of Project Everest. Project Everest aims to develop fully verified replacements for the entire HTTPS ecosystem and verify that working together, they really do provide the abstraction of a secure communication channel. To wrap up, with EverCrypt, you can finally have the car of your dreams. It's fully verified for correctness and security from standard side channels, and it has more crypto primitives than you can fit in your utility belt. It offers a fully modern API, which benefits developers of both unverified and verified applications. In building EverCrypt, we developed new techniques for verifying crypto code at scale without sacrificing performance. And of course, you can find our code, specifications, and tools online. With that, I'd like to thank you for your attention.